This is our final project submission, a deep reinforcement learning agent that plays Yahtzee, designed to eventually drive a UR3E arm with vision.
Hey, I'm Micah. I built the environment, which involves the rules, state, and action space.
I built the GUI, a PyQt6 dashboard to watch the agent autoplay.
And I train the agent. We'll talk through each layer, show evaluation, and address the feedback we got.
A Yahtzee game is 13 turns. Each turn you roll 5 dice up to 3 times, then commit to one of 13 scoring categories. Bonuses kick in for an upper section total of 63, and an extra 100 points for every Yahtzee after the first. The minimum score is 0. You can zero out every category, and the theoretical maximum is 1,575. In practice, a random legal player averages around 50, a skilled human around 230, and the mathematically optimal policy solved analytically is around 254. Our design doc target was 190 and our best agent hit 232. One more reviewer question. Are we training against ourselves? No. Yahtzee is solitaire. The only opponent is the dice. The agent learns from its own past games, but it never plays an opponent. The agent is given 2 things, a 24-dimensional description of the current game state, and a choice between 45 possible actions. The state vector is basically a compact summary of everything the agent needs to know. It includes the count of each die phase, a 1 hot encoding for which roll of the turn we are on, flags showing which scoring categories are still available, the current upper section progress, and whether the Yahtzee bonus is still possible. A question we got was why there's so many actions. The reason is that the action space is split into 2 parts. One is actions 0 to 31 are the hold or reroll decisions. Since there are 5 dice, each die can either be kept or rerolled. So that's 2 to the power of 5, which is 32 possible keep patterns. We give each of these patterns its own action. Then actions 32 to 44 represent the 13 scoring categories. We use one flat action index rather than separating these into different action types because it made the legal action masking much simpler. At every step, the environment outputs a 45-dimensional legal mask. Legal moves get 0, and illegal moves get negative infinity. When this mask is added to Q values, illegal actions are automatically ruled out, so the agent never chooses an invalid move, and we do not need extra exception handling. Finally, our original reward design was deliberately very sparse. The agent received 0 reward during the game, and only received final scores divided by 100 at the end. That made the environment cleaner and closer to the real objective, but it also made learning harder. Matt will explain why that cost us marks and what we changed to improve it.
The network maps the 24-dimensional game state to 45 Q values, 1 per possible action, each estimating the expected future reward of that move. Action selection is cheap. 1 forward pass, apply a legal move mask, and then take the ARG max. The real engineering is in training, and there are 3 things that make it work. Firstly, we use prioritized experience replay. We store past transitions in a sum tree replay buffer and sample them in proportion to their TD error, the gap between what the network predicted and what actually happened. Because Yahtzee's only real signal comes from rare terminal transitions, prioritized experience replay lets us replay those informative moments far more often than uniform sampling would. Secondly, we use double DQN. We keep 2 networks, an online network that learns, and a frozen target network that sets the training targets, and we sync these every 1,000 steps. This decouples action selection from value estimation and breaks the overestimation feedback loop, the cycle where the network chases its own inflated Q values and the scores diverge. Finally, we used masked next state argmax. When bootstrapping the target, we apply the legal move mask to the next state as well. If we skip this, the bootstrap can select an illegal action and the network hallucinates a Q value for it, and the error ends up propagating backward through the training. But with the mask, the loss stays at about 0.001. There are 3 key reasons why we picked DQN over PPO. Firstly, our action space was discrete. Secondly, the problem was relatively small and structured since we had all the rules to Yahtzee. And finally, we wanted to benefit from off-policy learning with replay data. In terms of our training and evaluation, we designed basically 3 models. The first 2 were sparse rewards, and Model 2 beat Model 1 because we added prioritize experience replay. Model 3 is almost the same as Model 2, except we added reward shaping, so we started with dense rewards instead. Instead of 1 terminal reward, the agent gets the score added divided by 100 for every round it plays. This results in the same reward per game, but it's redistributed across every single round where it was learning. Model 3 averaged 224, clearing our 190 target by episode 30,000, about 25 minutes on my CPU, and that was 88% of optimal play. Now, one reviewer said that the dense rewards give the agents more points, so the score isn't a fair comparison, but the reward is the training signal and the score is the metric. So it ends up being a fair comparison because we average the final Yahtzee score over 100 greedy games. So the shaped agent doesn't score high because it received more rewards. It scored high because it learned a better policy, and we measure that on the same scoreboard. And then also another reviewer pointed out that the training curves look like they converge early and we could have used fewer epochs, and we do agree, but we just wanted to bump our score up just a little bit more.
This is the dashboard running in autoplay with our third model. You'll see 3 panels. On the right, the dice panel, the current roll and a keep re-roll toggle on each die. In the center is the scorecard. On the left, the Q value chart, the network's confidence over all 13 scoreboard actions, updated in real time. The longest bar is the action it's about to pick if it chooses to score. Otherwise, there are another hidden 32 actions that relate to holding the dice, which may be chosen if the confidence is higher than scoring. Watch the chart through 1 turn. On roll 1, agent decides which dice to keep. By roll 3, holds become illegal, the mask zeroes them out, and the score bars take over. When the dice form a full house, a score full house becomes the best choice for the agent and is chosen. The GUI is a passive observer of game state. It doesn't drive the agent. It reads the environment state, asks the agent for an action, steps the environment, and then re-renders. What we have developed is just a brain. The engine, agent, and GUI run end-to-end on a laptop with no hardware needed. The plan was always to wrap the brain in real perception and actuation.
Everything is on GitHub, code, model, checkpoints, design doc, and also a long-form agent walkthrough.
The portfolio page links the demo video and the trading curves.
Thanks for watching.